Okay, here's a quick video. Those of you who've been asking about problems 8 and 9 on the practice exam, it would help if we had finished the lesson on Thursday before house day. So here it is, at least some of it. If you look at problems, so this is the handout from Thursday, 1-9, and if you look down here, you'll see the only difference between the first part of problem 2 here and problem 3 is the angle. In the first case is 30 degrees, and we know all about 30-degree triangles. We have the proportions memorized, so the side across from this we know is a half of the hypotenuse. For a 20-degree angle, we don't know what this side is relative to the hypotenuse, or the other leg for that matter. So for these problems, when the angles aren't the special angles, you'll have to look them up in a table, and I've given you a table on the back of the practice exam, which I'll show you in a moment. But for now, let's see if we can find the hypotenuse here for this 20-degree right triangle. So this across from 20 would be the opposite to 20, and so this would be the adjacent side, and then across from the hypotenuse here is across from the right angle is the hypotenuse. So we want to use a trig function that involves something we know and something we want to know. We know the adjacent, we want to know the hypotenuse. So adjacent over hypotenuse seems to be the right relationship, and that's the cosine of 20 degrees. And so we fill in what we know, which is the adjacent side, 6 root 2 over the hypotenuse. And then if it were 30, 60, 90, we'd pull the ratio from our memory, but since it's not, we have to look it up. So we go down to the table here that I've provided on the back of the practice exam, and you find 20 degrees. And you look up the cosine of 20 degrees. I can't remember now, is it cosine or sine? We're using cosine. So back to here, we find the cosine of 20 degrees. Cosine here is in the first column. Is the cosine of 20 is right there. So it's 0.94 or 94%. So the adjacent side to a 20-degree angle is always 94% of the hypotenuse. So this is 0.94. And we can cross multiply and get 0.94 times h is equal to 6 root 2. So what we're doing is the same thing we did with special right triangles, but now we're using ratios that we look up in tables as opposed to ratios that we pull from our brains. At this point, you have what's called a calculator-ready expression for h. In other words, the algebra is done. So up here at this level, you have not done the algebra yet. It's a class in algebra. Still not done the algebra at this level. Here you have. So on an exam without a calculator, you could stop right there. If you have a calculator for homework, you can punch it in and find the decimal approximation for that ratio. And then we have to find the other side. So we found the hypotenuse. We know the adjacent side. So to find the opposite side, since we have this one exactly, let's use opposite over adjacent, something we know here and something we want to know. So take the tangent of 20 degrees. That's equal to the opposite side, which we don't know, divided by the adjacent side, which is 6 root 2. And now let's do the algebra before we do the lookup. So cross multiply 6 root 2 times the tangent of 20 degrees is equal to O. That's not a 0, that's an O for opposite times 1. So it's a little confusing. And then we're done. We have a calculator-ready expression for the opposite side, but we have to look up the tangent of 20 in the table. There's 20 degrees. The tangent is over here. It's 36.4% or 0.364 is the relationship between the opposite side to 20 and the adjacent side. So this is the side that we're looking for, the opposite, so we know it's not 0, is equal to 0.364 times 6 root 2. And again, we have a calculator-ready expression. On an exam without a calculator, you would stop right there. In homework, you could get the correct answer. You could get the decimal approximation. So in problem 4 here, we're just asked about the relationships in a 15, 75, 90 right triangle. So just draw a right triangle. It doesn't have to be to scale. Doesn't have to be accurate, really. Helps to be close, but that's 75, and that's the smaller angle. That's 15. We know it's the smaller angle because this looks like the shorter side of the two. And the long leg, which is across from the bigger acute angle, would be 10, so that's your opposite side. And the short leg over here, the adjacent side, we don't know, and we don't know the hypotenuse, but we have a table that gives us the relationships. And we're supposed to find the short leg, which is the adjacent side. So we know the opposite, something we know and something we want to know, opposite over adjacent again. So take the tan of 15 degrees, and you'd get the opposite side. Wait a minute, that's the tan of 75 would be opposite, which is 10. This is opposite to 75 over the adjacent side. The problem is when you go to look it up in a table, the tangent of 75 is not in there. The table only goes up to 45, and that's because every angle in a right triangle lives with its complementary angle in the same right triangle, so you really only need the angles up to 45 to find any ratio, which is to switch our perspective here. So instead of using that bigger angle here, we use a smaller angle up here, 15 degrees, and then just reassign relative to that. So relative to that, if that's a 15-degree angle, this side is now the opposite side, and this side is the adjacent side relative to 15. So if we want the tangent of 15 degrees, we just go through here and rewrite the opposite side, which is what we don't know, divided by the adjacent side, 10 is which we do know, and now we can cross multiply or just multiply through by 10. You get x is equal to 10 times the tangent of 15 degrees. Again, calculator rate expression, you're done. All the algebra, all that's left to do is look up tangent of 15 degrees in the table. And the tangent of 15 degrees is here, 0.268, I believe. Yep. Go here, and x equals 10 times 0.268, which we can actually do without a calculator. It's 2.68. Move the decimal place, and that seems about right. If it were a 30, 60, 90, the tangent would be, well, it's hard to say with the square root of 3. You don't have a good feel for that. So, but it seems reasonable. It's certainly smaller than the 10, which it should be. Let's move on to the next one here. 22, 68, 90. Again, just draw yourself a right triangle. Don't worry too much about whether it's to scale. 68 looks like the bigger angle. 22 is the smaller angle. Let's use the smaller angle because that's the one that's going to be in a table relative to the smaller angle. That's the opposite. That's the adjacent. That's the hypotenuse. And so we wanted to know the length of the short leg relative to the hypotenuse as a percentage. So we went the part to the whole, the short leg being the part, the hypotenuse being the whole. The short leg is the opposite in this case, across from the smaller angle. And so we want to know what's that percentage. And so we just look it up. It would be the opposite over the hypotenuse would be the sine of 22. The sine of 22 is the opposite side, which is the short leg of this triangle divided by the hypotenuse. So the answer to the question is really just the sine of 22. Just a fancy way of asking what's the sine of 22. There's 22. There's your sine column. Come down here, 375, so 37.5%. 0.375 is 37.5%. So in every 22, 68, 90 right triangle, the short leg will be 37.5% of the hypotenuse. Notice that it's less than 50, which would be the case in the 30, 60, 90 right triangle, because as that smaller angle gets smaller, the side opposite gets smaller, so it's a smaller percentage of the overall total. So it dropped from 50% down to 37.5% when we went from 30 degrees down to 22 degrees. And lastly, let's look at a 3, 4, 5 right triangle. Everybody knows these guys based on their side lengths because it's a Pythagorean triple. 3 squared is 9 plus 4 squared is 16 equals 25, which is a perfect square. But nobody ever asks what this angle is here or what the other one is. Let's use this one because it's the smaller angle. You know it's the smaller angle because it's across from the smaller side, smaller leg, and it will be in the table. It's commonly assumed by some students that this is a 30, 60, 90 right triangle. It's not, because 3 is not half of 5. In fact, 3 is more than half of 5, so this angle here is bigger than 30 degrees. The question is how much bigger. So the best way to start out is with a trig ratio like the sine. The sine of theta, we have all the sides here, so we can pick anything really. Sine of theta is the opposite of theta, which is 3, divided by the hypotenuse, which is 5, which is 0.6. So we just look up in the table, we back out. We start with the sine as 0.6, and we figure we go backwards to figure out what the closest angle is, and the closest to 60, 0.6 is there. So to the nearest degree, it's actually a little bit smaller than 37, but it's pretty close to 37 degrees to the nearest degree. So this would be, theta is approximately 37 degrees, and then if that's 37, this is the complement, 90 minus theta, which is 90 minus 37 is 53 degrees. So this is a 53, that's 53, and that's 37. It's a 53, 37, 90 right triangle, a 3, 4, 5. Close enough. It's not exactly, but it's pretty close to what it is. These problems here are just like that. Again, this is all identical to what we did with the special right triangles, except the ratios are coming from a table as opposed to from memory. That's the only difference. Let's just do one of these. Let's try B here. Again, using this template over here on the right, little a is across from side, little a is across from angle big A, so this over here is 2 root 3, and angle B is up here, so this angle here is 50. That's 50, this must be 40, because that's a right angle, and so we use the smaller of the two acute angles, 40, and let's start off by looking for the hypotenuse. The hypotenuse, this is the opposite relative to 40, that's the adjacent. So we go with the sine of 40 is equal to 2 root 3 over the hypotenuse. Cross multiply and you get 2 root 3 equals h sine 40. And now divide through by sine 40, treating it as a single number, which it is, and you get 2 root 3 divided by sine 40. The SIN, the two parentheses, the 40, and the degree sign all together represent a single number, which we're going to look up in a second, so we can divide through it just as we could if it was an integer. That's h. And then we look up the sine of 40 degrees. By the way, this is a calculator-ready expression here. The algebra is done. That's the most important thing on an exam. The next most important thing is to be able to look up the sine of 40, which I'm sure you can all do. 40 is right there. 0.643, and the least important thing is to be able to plug this in a calculator. Oops, important not to make a mistake. 0.643 is the hypotenuse. And similarly, you could find the other side. So we found this side now, we know this side. You could use a trig ratio. I would use the tangent again, because a tangent would involve this side, which we know exactly. You have to work with, don't have to mess with this ugly ratio down here. In problem like C, where you get side lengths only, again, little a here is 3 and C is 9, and so it's not clear which angle is smaller, but I think it's this one. So let's start with that. The sine of theta is, I'm using the smaller acute angle because I want the number to be in the table, so the sine of theta is a third, which has decimal is 0.333 repeating. So we want to find the closest angle to 0.333 repeating, which would be in the sine column, which would be here. That's close you're going to get. It's a little bit closer than 20, so 19 degrees is the closest whole number angle. So theta is about 19 degrees, which means that this angle up here would be the complement. So if this is 19, this one would be 71. So 90 minus theta equals 71 degrees. And you could find this third side here either by setting up a ratio or using the Pythagorean theorem. Let's skip ahead here and look at this rhombus problem, since most of you have forgotten what a rhombus is. It's just a square which has been shoved over, so it's no longer 90-degree angles. It's an equilateral, it's a quadrilateral, a four-sided regular figure with equal length sides. So the sides are all the same length, but the angles are not 90 degrees. So these sides are all 5, and the height, which is this length, this height right here, that distance is we're told that's 4. So this guy right here is a 3, 4, 5 right triangle. You can tell just from looking at it that 25 minus 16 is 9, square root of 9 is 3. And then to find this angle right here, we just use a trig function. So let's actually find this angle, because which is the smaller. So this is the smaller angle here, isn't it? Because it's across from the 3. So let's find this angle here. That angle there, the sine of that angle. Actually, we know the angles already, don't we? 3, 4, 5 right triangle. The angle's right here. The smaller angle is 37. The bigger angle is 53, roughly. So this angle right here is 53, and this one's 37. So, and then this is 90 here. So this whole angle here is 53 plus 97. So if you redraw the thing, this whole angle here is 37 plus 90, which is 127. And this angle here is 53. And these angles over here are the same. That's also 127. And that's also 53. Those are the angles for the rhombus. Hope this is helpful. We'll talk more about this tomorrow in class. Have a good evening.